one street
Yeah.
in San Francisco.
Yeah, like if you look at the distribution, it's actually rather interesting. Like I say some of them actually have, some of them are actually very, very strong related to the geographic location. Some of them have absolutely no relation to the geographic location.
Okay, it's 6:30, so you can go ahead and get started. Today I'm going to review and do a few practice problems on support vector machines and kernels, which I know you've seen a lot of recently, but yeah, so talk about support vector machines and then in kernels a little bit, particularly in relation to support vector machines, but then also general kernel properties. So we'll go through a few practice problems there. On your upcoming homework assignment, you have several kernel questions that are similar to what we'll do today. So by this point you are well aware of this, but suppose you need to classify some points and you want to choose between like this line and this line, which is intuitively the better separator. This one, yeah. And so intuitively, why is that? Well, here if you have the first one, sure it classified or it can separate a set of points. But say you had a slight perturbation in the data, and that point moved just a little tiny bit over, not all of a sudden it's going to be misclassified. But if you had this other one here, and the point moved the same amount, it's still on the correct side. So this is the intuition for why maximizing a margin between the data or between the classes is useful. Yeah, so that's the margin. So everything that lies on the margin we call a support vector. For SVM, this is helpful because if you want to classify a new point, you actually only need to hold on to the support vectors. You don't need to keep your full data set in memory. Yeah, and only moving the support vectors changes the size of the margin. So just to go through how you can represent the decision boundary, you choose this plane that separates your classes by this W vector and then the intercept B. And as you saw in class, there are a few different ways. Maybe you include the B, maybe you don't. If you center your data first, then you can assume that you don't have to have the B there. And then on one side, everything that is greater than or equal to 1, which is going to be this line, you say is positive. Everything less than or equal to 1, or sorry, less than or equal to -1 is in the negative class. And for the hard margin case, you just assume that nothing's going to fall into the margin. You don't know what to do in that case. So then if you get a new point, suppose you just do this w dot x plus b, and say for this example we saw it was 2, so that's positive, it's a positive example. This other example is -15, so we're going to classify it as negative. And another thing here, if you look at the exact magnitude of this point, it gives you an idea of how confident you are in this prediction. So here it was 2, it was pretty close to the boundary. There it was -15, it was farther away. So you're more confident of a point if it has greater magnitude for that value. Yeah, so just your decision rule is the sign of this quantity. But what we want to do from our training set is to find the values for W and B. And we do this by optimizing. The particular form of the optimization, right, is we want to maximize the margin, which is equivalent to minimizing the norm of W. Subject to constraints that everything is here not only correctly classified, but outside of the margin as well. So here it's, yeah, that's the equivalence. So it's, as Barnabas talked about, it's convex optimization problems, quadratic program, easy to solve. However, what if your points are not linearly separable? So one idea is to transform them to a higher dimensional feature space, and maybe then they would be linearly separable there, as we can see in this example. That was just say if you just like squared them. But maybe we don't want to transform to a higher dimensional space, just so they'll be linearly separable. In that case, you might overfit to your training data, right? Because if you go to a high enough dimensional space, you can linearly separate anything. So we want to think about other ways to deal with non-linearly separable data. So here, in this case, not linearly separable, but we still say, well, we can draw this line here to mostly separate things. And suppose we had the same margin as before. So in the previous example, these were our support vectors here, because we're allowing things to be within the margin and even misclassified. This is called soft margin, SVM. So we have some things that are misclassified. They are also support vectors. And then some things can fall within the margin, and they're also going to be support vectors. So the new optimization formulation, it's kind of similar as before. You want to minimize this W transpose W, but now you have this weird term on the end there, and subject to your same, you had this, if you chop off the minus psi I, you had that same thing before. But really what these psi i's are getting at is how far either into the margin or on the other side of the decision boundary are these points. So this here, they're technically called like slack variables. So they allow the points to be within the margin and on the wrong side of the separating hyperplane, but there's a penalty placed on it every time you do. So they're constrained to be non-negative, so every time you have to add something here, that's going to mess up your minimization objective. So that's what we mean by there's a penalty to them. Yeah?
So in real life, how do we choose C?
So that's one of the things that gets into like model selection. So over time, you'll find that like when you're learning about these algorithms, there's kind of a lot of things you're going to have to choose. So a common way of choosing something like this is through cross-validation. So you'll divide your training set, like subdivide your training set, and like train on part of it, and then test on the other part of your training set, and then look at that held out test error to choose. Each of the partitions you use a different value of C, and then whatever gives good error on your held out part is you'll say, well, that's a good value for C, and then that's how you'll choose.
So just try everything under something.
Sorry, what?
So it's just like trying everything under something good.
Yeah, well, kind of. Well, I mean, it's more principled than that, right? You're not just trying everything on all of your data. You're specifically, holding some out. That's the whole point of, wanting to make sure you separate your data into all these different subsets. But yeah, the idea is to look at kind of, in practice, for this particular data set, what works well generally. So this optimization formulation for the soft margin SVM is equivalent to minimizing here, this loss function is the hinge loss, plus you have this regularization penalty on W. So just broadly, you all know this pretty well by now, but loss functions kind of capture how wrong a model that we're building is. So ideally, you want to minimize this quantity. A natural choice for the loss function for classification is the number of misclassifications. That's called the 0, 1 loss. So that's what's plotted here. Basically, so here it's actually assuming that your classes are labeled 0 and 1. So if you're looking at this product y dot y, if it is, well, basically, like if it's, so this is the region where they don't match up. Here, let me just put the, So if y does not equal y hat, the true value doesn't equal your prediction, you incur a loss of 1. Otherwise, if they do match, no loss. That's why it's called 0, 1 loss. And you can see here that the hinge loss in green is an approximation to the 0, 1 loss. It's nice, it's convex, so you can see here, like if you were to take like a point over here and a point over here and connect them with a line, you would see that this curve doesn't lie below that line, which means it's not a convex function. So this is one of the, well, in general, lots of times people will relax the 0, 1 loss to get a different loss that's easier to work with computationally, and the convexity is oftentimes one of those reasons to do that. So you can see that the hinge loss kind of characterizes or exactly how wrong your prediction is. So here, if you're like way off, it gets much higher than the 0, 1 loss did. And then as long as it's right, it doesn't care about if it's right or really right, you get 0 loss either way. So just to remind you about duality, which comes into play for SVMs, you have this primal formulation subject to these constraints. You can form your Lagrange dual function, which is your objective plus these Lagrange multipliers times each of your constraints. And then you know that if you define this optimization problem as maximizing the Lagrangian to be just the value of your objective, if the point x satisfies the constraints, here that was the inequality constraints g of x and the equality constraints h of x, and otherwise it's infinite if x does not satisfy those constraints. So here you know that, so always the primal is greater than or equal to the dual. This is weak duality, but in some cases they're actually equal. Yeah, so for convex optimization, if these KKT conditions hold, then there's strong duality, the primal equals the dual. So an important thing in the KKT conditions to point out, particularly for SVMs, is that here, this one is, remember, is called complementary slackness. So that's saying that at the optimum value, your Lagrange multiplier alpha times here, this g of x was your inequality constraint. That equals 0 for everything. So here, for SVM, the alphas are non-zero only at your support vectors. Yeah, so if you were to go through and do this process for SVM, which you saw in the lecture, you would get an equivalent formulation. And so then if you were, because you know the KKT conditions have to hold, you can, here's the stationarity, we know that the gradient of the Lagrangian is 0, so you can solve for your different variables that you need, and then here you get this equivalent statement of your soft margin SVM. So we're going to, now that you have been reminded of the dual formulation of SVM, we're going to take a detour into kernels and go through some examples that are going to be similar to what's on your homework, and then we'll come back and, I mean, you already know the punchline of this. The punchline is that you can use kernels for this dual formulation of SVM, but yeah. So here in the nonlinearly separable case, we were going to say we take this transformation phi that brings us from our original data to a higher dimensional feature space. It can even be infinite. And so, especially when it's infinite, that's when the kernel trick is handy. So a kernel is basically a legal definition of a dot product. So this kernel, it defines this implicit mapping from your input space to this higher dimensional phi space. So an example here is the polynomial kernel, where if you have a dot product of two vectors, raise it to any positive power. So suppose we just take the particular case where you're raising it to the second power, and the dimension of each vector you're looking at is 2. So here your implicit mapping, you see if you do the implicit mapping from R2 to R3, where the first dimension in your phi space is x1 squared, and then x2 squared, and then square root of 2, x1, x2. You can see that when you multiply phi of x times phi, or take a dot product between phi of x and phi of z, you end up getting here this definition of the kernel. So that's an example of this implicit mapping giving rise to your kernel function. But it's important to remember that you think of phi as an implicit mapping. The whole point of kernels is you want to avoid all of the computational overhead of going through and doing this mapping. So we're going to see how we can compute kernels without using the explicit mapping. And this works for many machine learning algorithms, including, as you know by now very well, SVM. Oh, yeah, that's all. So the main properties of a kernel is it's symmetric and also positive semi-definite. And if you want to, oh yeah, so here in this notation, K is the gram matrix of the kernel. So basically it's going to be an n by n matrix where the ijth entry is the kernel function applied to xi, xj. And another important thing to keep in mind, so if you want to calculate something is a valid kernel, you can go and look at the particular properties that it had to satisfy, or there are some operations that you can prove kind of like ahead of time, still preserve the symmetric and positive semi-definiteness of a kernel. So here, I have a few examples. There are more extensive examples on the lecture slides if you want to go back and look at those. But here you can see that if you add two valid kernels together, that's still a valid kernel. So yeah, you can see. Yeah?
So you said when you showed like the positive semi-definiteness, you represented the kernel like as a linear transformation. Can you always do that? Or like how does that make sense in terms of like dot products?
So here the kernel is an n by n matrix, because it's a pairwise operation applied to all of your, like say each row in each, or you have a collection of vectors, and so you put that same collection of vectors on your rows and on your columns, and then the, like I said, the ijth entry of K is the kernel applied to your ith row and jth column. Not, okay. So when I said column, I meant like the vectors that you were looking at, not the columns of K itself.
Okay, yeah.
Does that
That's better.
make sense? Okay, okay, good. Yeah, so like if you add two kernels together, if you multiply by a positive number, you can add a positive number, multiply the kernels together. Yeah, so if you want to show that a kernel is valid, you can check that the two main properties, the symmetry and positive semi-definiteness, hold, or you can use these kernel closure rules. So you have several questions like this on your upcoming homework 3, so I thought we could go through a few examples now so you can get comfortable with the idea of what's going to happen. So here's the first example. We're going to say this kernel function is defined as the square root of x times z. Is this a valid kernel? Okay, I see a couple head shakes. Does anyone not, oh, okay, does anyone think it is valid? You might be right. You think it's valid, okay.
So if you just map x to x, that's a mapping from 1D to 1D. It's so kind of.
Huh?
So this would be a dot product between phi1 of x and phi2 of z, where phi1 maps x to its square root and phi2 is just the identity.
Okay. What about, all right, does someone who thinks it's not a valid kernel want to say why? Yeah.
X equals 2, Z equals 3.
Yeah, so what property fails for that particular example?
Symmetry.
Yeah, symmetry. So, like he said, so suppose x and z are not equal to each other. Then if you do k of x, z, that's not going to equal k of zx. Does that make sense? Okay. Yeah, so things to keep in mind when you're doing your homework. So here we have another example that is literally just the dot product of x and z. Is that a valid kernel? Yeah, so it's symmetric, it's positive semi-definite, you're good. Here we have another example, the dot product of x and z raised to the 8th power plus 10. Is that a valid kernel?
Yes.
Okay, does anyone want to explain why?
Using the closure properties.
Right, yeah, so So actually, like another of the closure properties is that you can raise a kernel to a positive power, and that works. But you can see that that kind of just comes through induction of multiplying these two kernels together. So if you have a valid kernel multiplied by itself, that's another valid kernel, and just continue doing that. Yeah. So you're applying this rule and then also this shifting rule there. So yeah, that one is also valid. Yeah, so there are a few like true-false questions like this on Q&A for you to do for your next homework. Oops. So here we are back to the dual formulation of SVM. And you can see that the important thing to notice here is that your points, your x's, appear only as dot products with each other. So just replace that with the kernel. So you can see here that this kind of gets back to the point of why you don't want to explicitly compute this mapping phi, because really all you need is the dot products of phi x and phi z. Because in this case you can just, all your calculations where you would have the dot product of xi and xj, just replace that with the kernel function applied to xi and xj. So the kernel trick is important and useful because they allow you to map to a higher dimensional, more complex space without going through all the computation of actually transforming your features into that space. Instead, you can just do this simple operation to get what's equivalent to the dot product. Yeah, you don't have to compute transformations. So here you can see with kernels, you can just go through and every time, yeah, for these points, go through and just compute the transformed value to get your solution in the kernel space. So okay, I'm not sure, in class did you go over multi-class classification with SVMs at all? Not really, okay. So we're not going to go into much detail here, but I'm going to help you think about some ideas that you might want to approach multi-class classification, because lots of times, right, you don't want to, classify just 2 classes. You maybe want to classify 39 classes for whatever reason. Maybe you have a number like that. It is 39, right, in your project? Okay. Not completely random. So suppose here, I'm not going to show 39 examples, just 3. But there are a couple, before we go through and talk about them, do people have ideas for how you might go about approaching a problem, a multi-class classification problem with SVM?
Do it pairwise.
Sorry, what?
You just do it pairwise.
Pairwise?
Process.
Yeah, so, Eric, could you go into more detail what you mean pairwise? Just like, okay, yeah. Maybe for this example.
Filter out points that are not class A or class B for some 2 classes.
Oh, okay. So you're saying like completely remove the blue points.
Yeah.
Get between these 2. Yeah. So that's one. Does anyone have other ideas? Okay. An idea that's very related to his is that instead of just like taking out the other points, you can still reduce this to a binary classification problem, but maybe first focus on all the blue points and sort of make your binary classes blue, not blue, and then you would draw a line there. So yeah, this is the only reason I'm talking about this one first instead of yours is that in the slides. That's how I put it in. So there for each class, you're going to train an SVM to distinguish between that class and all of the other classes. So if you have k classes here, you're going to end up with k different SVMs that you do. So here you have green versus not green, red versus not red, blue versus not blue. So here, when you have these k different SVMs, you're ultimately going to assign a point to the class that gives the highest value for the decision function. So remember before how just the decision boundary was going to be the sign of W transpose X plus B, but we noticed before that kind of the magnitude of that value indicated how confident you were in that particular prediction. So here you would actually use the magnitude to make your ultimate decision if you're going to do it this way. So let's see, for an example, say like a feature that, or sorry, a new point that was like right here, you see it could be classified as red, it could be classified as blue, because it's on the positive side for both of those classes. But since it's really close to the red boundary, it's going to have that small confidence value. So here you would assign it to be blue rather than red. Another thing you could do is actually come up with an optimization objective that handles all of your classes together. So in a case like that, you learn all of your decision boundaries simultaneously, and you would get something like this for these 3 classes. And so again, you're learning the parameters for all the hyperplanes together, but you still end up with these different kinds of like piecewise decision boundaries. And then this is exactly what you said. Consider classes together. So here, these lines are completely ignoring the blue points and looking at the green and red. And then you have ignoring the green and separating the blue and red, and then ignoring the red. So here, the strategy that you use to assign a new point to a class is you vote. So you get your new point, and you would take each of the values that they gave, and then you would actually vote on, like if most of the time it said to, let's see. So suppose you had a point that was here in the blue region, so probably blue. But like if you looked at this one that separated the red and green, you would say it's a green point. If you looked at this one separating blue and green, you'd say it's a blue point. This one separating the blue and red, you'd say it's a blue point. So you had 2 votes for blue, 1 vote for green, so you're going to say that it's blue. Does anyone have any questions on multi-class classification? And so honestly, when you're doing this yourself, you will probably just use a package that someone else has already written. Because it's going to be faster, it's going to be right. So if you haven't tried SVMs for your project, that's definitely a thing that at this point you understand them and you can use it. So you can see how that goes, and you can let me know how it goes, because the only baseline I tried was naive Bayes for your project. Yeah?
There's naive Bayes?
So it does significantly better than chance. I'll see about uploading it to the scoreboard just so you see what the baseline was. So like, I don't remember right now the exact error or whatever of it, but so significantly better than chance. So, here's the thing maybe we could talk about, because I know there was a Piazza question about like how the scores are going to be determined, and I think people are you just like worried about your grades?
We're confused about how it's getting scored.
Okay, so part of that is like we were trying to be sort of intentionally vague to wait and see how everyone did, because we don't want to say like, here's this hard threshold, you have to get this, otherwise, like you have to get this to get a B or whatever, and then if no one gets it, like if no one, we're not going to fail everyone. Ideally, like no one will fail, right? So we kind of wanted to wait and see how people were doing, and so usually there will be like sort of a region of performance that a lot of people are able to get, and there might be some outliers either way above or way below the people who, I don't know, put in a lot of work, did something really complicated, or just got lucky. And then, on the other end, maybe people who didn't put in as much work as they should have. So the idea was you're going to kind of wait and see how that played out. But if you want to get a sense for maybe how good your classifier is, you can think about some baselines that you could try out and submit. So does anyone have, you can just like brainstorm ideas for baselines now if you want, because I also did. So I had a few ideas that I did before, and we can see if you can think of those, or maybe you'll have other ones. Just like, what's a really simple thing that you could
from 1 to 10. What is it? 30?
Yeah, so you could choose something randomly. That could be one type of baseline. But what would, so right, when you're submitting your file, you're not submitting predictions for everything. You're submitting your estimated probabilities that each test point is in each class. So what would random probabilities be, assigning a point randomly, what would that be equivalent to if you were to put your estimated probability for each class?
They're all the same.
39 for everything.
Yeah, 1/39 for everything, right? So that's one type of baseline that you could try to see if, because that's like, to see if you learn something out of what you're doing, right? So the thing that I mentioned earlier, if people are getting infinity scores, that's actually because they've predicted 0 probability for something, for an instance that is actually that true class. So let's see, your exact scoring function, right, is yeah, this was all I had in the presentation, so we can talk about your project now.
I think you could submit a 1/39 file for all everything.
Okay, I'll talk about
I want to see what the test is.
the baselines that we might think about using, and if we'll release those to you all. Oh, there we go. Okay. So your score, it's not just the error of your classifier. We're actually interested in more of your overall prediction of what.
So the top 3.
So we're not just interested in if you're going to predict the correct value, we're interested in how confident you are that this new test point might be each particular value. So what this is actually looking at is you're taking the log here. This is from your predicted probability file, but it's taking the your predicted probability for the true class. So say your example, let's say we have just like 3 points, 3 classes. So here, class 1, class 2, class 3, for this, your first test point, you say, oh, there's 80% probability it's class 1, 15% probability class 2, 5% probability class 3. For your second point, you say 100% probability class 1, and so 0% the other ones. Yeah. Oh, you don't have to, I think this was in the thing, you don't have to normalize because we normalize before we can do the score anyway. So here, suppose that the true labels, this first one was class 1, and this one was class 2. So you can see here when you compute the score, when you take the probabilities that you're going to be looking at, here this is the true class. So the probabilities you're going to be looking at, this one was C1, so you're going to look at this probability. This one was C2, you're going to look at this probability. So you're going to sum up log of 0.8, which is some negative value, fairly small, and then log of 0, which is negative infinity. So the sum is going to be negative infinity, you take the negative of it, then you get a score that's infinity. And so you can see here, that it's because we're looking at not only if you got the class right, but how confident you were that you did get the class right. So suppose here, right, so like I was saying at the beginning, it is possible to get a 0 score, or score of 0, but to do that, you kind of have to know exactly what everything is, because then, so suppose this example, the first one was class 1, so we're going to say it's 1 probability. The second one, class 2, we're going to say it's 1 probability. So then, again, you're going to sum up the same values. Log of 1 plus log of 1 is 0. So you can get that. So, yeah, if you know exactly what everything is, it is possible to get a score of 0. But you can see here that you're like infinitely penalized for putting 0 probability on something that is actually true. So maybe you don't want to put 0 probability for anything, even if you think it's very likely, right? So there's one class that has only like 1 or 2 examples in your training set. So it's probably not going to appear very often in your test set. But if it does, and you say it has 0 probability, well, you're going to have an infinite score. Yeah?
I was just going to say, I think like the easier thing for us just to get a better sense of like what a good score is just like if there are some baselines submitted to the leaderboard, because that's just like a because right now there's only like 5 submissions, and I think a couple of those are actually just like
people. Okay, sorry, you didn't mean your limit.
5 people who are on the leaderboard, and I'm feeling that people are going to start submitting a lot like the Wednesday before it's due.
Okay.
Like, up until that point, there's not really going to be anything on the leaderboard, and so it's kind of hard to tell like what is like, oh, I'm doing really well or not, because like the score number itself, like it's very based on the data set, right? Yeah. So just the number itself isn't like
Okay.
So if we just get some really like basic like, okay, this is the score that you would get if you did like just this or like just this and something, just so we can like.
Okay, like get a sense for how good you are with. So is the idea you don't want to waste a submission of your own just to get a baseline value?
Because there's no point in like all of us doing that, right? Because then it's like as if everyone has like.
Well, I mean, at least then you'd have the baseline, and you could all like be this cohort of people who are all not going to fail together.
That do score 0 submissions on the score.
Yeah, those are infinite.
Those are infinite? Like,
Yeah, at least the ones that I've looked at, yeah. So how likely is it that someone got everything completely right?
So does the 2.59 mean they got it?
Yeah, so if it's something like that, then that means that they did get a valid score, or like an actual numeric score. But so I'll talk with the other instructors about posting these baselines for you all to see, but before we do that, so Emily mentioned one idea would just be this uniform probability for everything, so 1 over 39 for everything. What would be maybe a slightly more advanced, but still really simple probability estimate that you could submit as a baseline? Yeah?
Just like a Bernoulli based on one variable or something, so just like, just like don't use everything, just do like a couple of the like simpler variables.
Yeah, that's one thing you could do, just look at a subset of your features. But even simpler than that, suppose your training set, you don't even look at any of your features.
Return the class probabilities?
Yeah, so the empirical probabilities on your training set, right? So there are some things that, what's the one that's the most, isn't there something that's like 70%? I don't remember. Anyway, there's, again, like one thing that appears only once or twice out of however 50,000, I don't know, however many points we give you, there's only a few very small number of examples of it. So you can still get a more, slightly more nuanced probability estimates, assuming the test data is drawn from the same distribution as the training data, and just to be open with you all. There was a data set, we randomly selected parts of it for testing and parts of it for training. So,
is this from Kaggle?
Yeah, it's from Kaggle. So, yeah. Okay, so given that it's from Kaggle, that doesn't mean that you should download it and match the training things to the true ones, or to what we gave you, right? Because if you wanted to cheat, you could do that. But that's like why we have that rule on the number of parameters you're allowed to set. So when you submit your code, we're going to look through and check if you cheated. So if you cheated, sure, you can get a score of like actual 0 and not infinity 0. But your grade will also be closer to actual 0. And I think that's what you care more about. So, yeah. But yeah, so the simplest examples where you don't look at features at all would be the uniform probability of everything or the empirical probability from your training set. And then if you wanted to get into like simple baselines that still weren't too complicated based on your training data, you could, like she mentioned, look at just one feature, 2 features, and then do, at this point, many classification algorithms. Naive Bayes, logistic regression, SVM. Now that you know about boosting, you do like boosted decision trees, which do like in a lot of these sort of like practical contests. Those are the things that do really well a lot of the time. So like boosting and then parameter tuning is what a lot of these like highly performing competitive machine learning things do. So you can do, like if you're interested in doing well, you can do one thing, but if you want to like try something new, so I don't know, how far along are people in your projects?
I parse the data.
Partially
Parse the data.
Oh, you parse the data. Okay. Yeah, well, you have to parse the data before you can do anything else. So, yeah.
So what are we supposed to submit? Just the prediction of the
Magic.
Yeah, so right now, before the due date, when you want to make a submission, all you have to submit is the your predicted probabilities for all of the test points. So of those, we take a subset that is unknown to you, and we do the score on that subset and put that on the leaderboard, and then there's another part of it that at the end will take that score, and then that's sort of like, that's the held out, the ultimately held out thing. You get no feedback on that.
So it says we split it for every submission. So is the split fixed or?
No, the split is the split is fixed. So
Okay.
I think it's half and half. So the same, is it like 40,000? Like the same 20,000 points are always going toward the leaderboard. The same 20,000 points are always held out.
So it's like just like line number 3, line number 5, line number 11.
Right. Yeah.
Okay.
Yeah.
Are you taking our best score?
I think that's the way AutoLab does it, right? It'll only keep your best score.
No.
Oh, it doesn't?
Last.
Okay, here. All right. I'm going to check to see if I can see. Yeah, I think it's fair to take people's best scores. Like, maybe you tried something and it didn't work.
So who wants to volunteer their submission and do the probabilities for each one?
Okay. I think we're going to be able to see all of the submissions. But if not, if you all could like keep a record of.
Oh no, we have a record on all labs.
Oh, on yours. Okay. All right. Let me see if I can see
It
that.
usually just puts the last one.
Okay, so the leaderboard is the last score. Okay. Well, all right. I wonder if there's all right. So.
See what it is. See what score we get. See what we get. We could totally try it. It takes like 2 seconds.
So I'm assuming that you all would also like to be able to see people's best scores on the scoreboard, right? Since that's what people are going to be graded on.
I mean, that's your plan. That's his plan. Submit it late. Eat everyone.
Oh, okay. Well, it depends how late, right? I don't think you're not allowed to use late days for the project. Is that
Wait, what?
right?
Presentation.
Oh, the presentation. Okay, sorry. Some of you are really invested in using late days in your project. Okay. Yeah. Like if I say it contradicts the official version, I'm obviously wrong. Ah. Okay. I can't see quickly if I'm able to have the best scores on the scoreboard or not, but I don't know. Maybe as it gets closer to the time, we can figure this out.
That's a
Okay, here, we can do an experiment. Is anyone here,
Exactly. That's how.
is there anyone here who has submitted more than once with a, because I didn't know if I just regraded, if that'll count as most recent then. Because if that happens, then if you submit it again and you see that your more recent score was worse than before, you can just email me or anything, and we can manually just tell it to regrade right then, and then maybe, hopefully, that'll bump it up to make that your most recent score. So let's see who. Okay. Wait, well, how do you know that submitting multiple times only takes your most recent score?
Because other courses do that.
Oh, other courses have done it. Okay. J Shen 2? No. CYL 1. All right, those are the only people who submitted twice.
Yeah.
So, okay.
We're always on other people.
All right. Yeah, well, we'll get that worked out. I'll see about releasing baseline results for you all to look at. So we talked about a few baselines. So has anyone started with a method to use?
SVM.
LibSVM, yeah. Just go ahead. Like I said, don't code it yourself. Just
Yeah.
use the correct work of others. Yeah.
Is the grading quite rigorous?
What do you mean?
Because there's a way to exploit the system by putting negative numbers in some places.
Well, I mean, okay. If you put a negative number in, it's going to try to take the log of a negative.
No. You're putting negative numbers for things that you know is not a true answer. And then you can put in a huge positive number in that, and then you can get P greater than 1. And then this will go to
P better than 1?
But you kind of
So we normalize everything
well,
before
sure.
we compute it.
Sure,
So,
but then when you normalize, if you add negative numbers, then you can still get something that you want.
That's not true.
So it's a way to exploit the system that, if you know
You will
the
get a
correct
zero
answer,
if you
sometimes you can get
normalize the
extremely good scores.
wait, okay.
He's gonna use the normalization.
Yeah.
Wait, you're gonna use
so
the
negative.
Because
Negative numbers
normalization, you have to add
normalizes.
everything together, and then the negative numbers is actually lower than the actual sum. So you can have one huge positive numbers and a whole bunch of negative numbers, and then you get P greater than 1. You get it correct.
if you make a submit a log, this would happen.
Wait, but okay. I think I'm still
Okay, so-
following, right? So it happens if you have a negative number here.
Yeah.
So you have a negative probability.
And then we normalize.
No. We're
No,
not having
that's the
negative
wrong
probability.
So it's like-
We don't choose that one. The correct answer is not the one which has a negative number in it.
Okay, well you still have to know the correct answer.
Well, yeah, but
he's
then
gonna
let's
boost
try it.
his score.
I don't know, the best score you can get is 0.
But then if you miss, you die. So.
Oh,
Yeah.
but then we got 20 submissions. So if we get 1 point something, and then
Okay.
actually
In
get
the end, the best scores, we're going to check all of your code manually.
No, it's not checking your code, but actually make sure to check the output doesn't have negative numbers, because that's pretty much cheating. You can get arbitrarily low scores to the point where you get negative.
Don't cheat.
No, you can get negative scores.
If the probability is 1 point something, then the log, maybe even 2 point something.
But you're not going to get, you're saying by
Yeah, you get the negative
normalizing
numbers,
it
yes.
in a way, but you would have to strategically put your negative numbers in
Well,
places where it's not that class, so you've already kind of perfectly classified it.
You have to
No, you can go negative infinity and then have
Oh, so you're just gonna try to choose one and be well, I have 20 submissions. Hopefully, at least on the first 20, I'll get the correct out of 39 classes. Okay.
Yeah. So just make sure to check the grading script, because I'm pretty sure it's something so that.
Okay. Well, at this,
Yeah.
okay, it's gonna be you. If anyone does it,
It'll only be you.
I'll put a check in that and then print out a message don't be a jerk. Yeah, but in the end,
Or just take the absolute values and mess it up.
Dang.
yeah, there we go. You're foiled. Yeah.
The
Don't even
best
have to
these
do the math.
people's done is 2.5.
What?
That's
But in
more
the end,
than-
we want to make sure that people get a nice grade. on their project.
And submit all that.
So, like, if everyone does pretty well and someone is like trailing and did terribly, that's probably because they didn't put in the effort and time. So in that case, could be deserved to give a bad grade. But generally, we're not going to screw everyone over. Yeah.
You said this was from our Kaggle competition, right? Have they released the scores of like?
There's a public scoreboard on Kaggle.
Yeah, there's a public scoreboard on.
Could we submit on Kaggle, see what our score is?
But this is part of the data.
What's the character?
I mean,
It's a
yeah, you
machine
could.
learning,
Is that scoring the same way that you guys are scoring it?
Yeah, that's the same
So
metric.
what is
they're
the top
using.
scores
So you
on
submit.
that?
I don't remember. You could look it up. Let's see. To give you an idea of like how well people on Kaggle are doing, there were. I don't remember the number of submissions. I vaguely remember kind of where along them they were when I submitted various baselines there. So say there were like 1,000 submissions. Just doing like uniform probability put you at like position 600 or something. Right, so there are people who are doing like worse than the most naive chance that you could do. And then doing like the empirical probability put you up maybe like 100 places higher or something. And then in the end...
Wait, I do see yours.
Oh, is that? Yeah, so I think... Yeah, so... Well, okay. A couple things there. That's on their held out test set, so no one has the labels to those. And so that particular one, that was for if I did, it was naive Bayes on a subset of features. Yeah, so I don't remember what the score was on your exact evaluation set.
It's like 1,000.
But yeah, I don't remember what the numbers were. But anyway, like there are people who are way better, but then also like a whole lot of people who are doing just terribly. So
Some of these features look like they're not going to help us at all, like seconds.
Huh?
Like the seconds portion of the
Just get rid of the seconds then.
or
Yeah, I mean, so part of this is like feature selection,
There's nothing
you
about properly.
know,
Yeah.
doing what you want. So,
Type
yeah.
times at 13.
But this is like an idea of sort of kind of like real, or I guess like applied machine learning. Is like it's not just a simple problem of, you know, I know for a fact I should use this particular algorithm and these features are what I have. You have to like, sometimes it's trial and error, yes.
We split into the time of the month, so beginning, middle.
Does anyone have any other questions or comments on the project?
oh,
Do you want to
Payday
talk about-
time.
should we split it up?
Okay. So this was all that I had planned for today, so we're done early.
You said the street names are useful?
We believe that it could be of use.
Oh, 500 block.
So the thing is, we ignore the block, but we kept the street names because some places are intersections, so they don't have blocks, so it makes no sense.
And some places are more prone to crime.
So like we just don't think the block has anything to do with anything, we just think